Well, hello and welcome to Doc Ontko's Physics Lessons. My name is Keith Ontko, and this afternoon what we're going to be doing is taking a look at capacitance. Capacitance is part of the unit on electric potential energy and electric potential, and capacitance, as we're going to see, allows us to store a charge, much like a charge is sort of stored in batteries, but we're going to be able to store a charge in a device called a capacitor that can where this energy, the charge, can be released very quickly and used for some purpose. In some of the examples, the things that capacitors are used in, one is if you've ever taken a picture and you had to use a flash for your flash camera, flashes use capacitors. A large amount of energy has to be released at a very, very quick amount of time for the flash to give off that bright light, right? And this would not be possible with batteries, because batteries, while they store a lot of energy, they don't allow that energy to be released all at once. Another example would be a defibrillator, right? We see these all the times now in buildings. We see them in schools and businesses, churches, all kinds of different places. And what a defibrillator does is it gives a charge to a body that is having some kind of heart issues, and allows the heart to get back in a rhythm. And it does this by giving an electric impulse to that body, or to that heart. And again, capacitors are used for this purpose. And so what we want to do is we want to look at capacitors. And over on the right-hand side here, up at the very top, we see the image of a typical capacitor. And we see some numbers on that capacitor. It says 47 microfarads. And it's rated at 450 volts. I wouldn't worry about that too much right now. But this is what a typical capacitor will look like. Capacitors can be very, very, very small, or they can be, reasonably large. But typically they're very, very small devices that we use in circuits for a variety of different things. They're also used in radios to tune in stations. They can be used for computer memory. They can be used for a whole variety of different things. As we get into electric circuits, which is going to come very shortly, the capacitor has a symbol that we're going to use, and that symbol that I've just put a square around here can be either one of the following. It can be this one here on the left-hand side, where you have a straight line with a curved line underneath it, or more typically, the ones that I use is two parallel plates stuck together. And sometimes we'll put a plus sign on one side or the other to indicate that that side of the capacitor should be connected to that side of a positive voltage source or battery. Okay, so this is the symbol over here. Over here, this is what an actual capacitor looks like, and the objects at the top are examples of what capacitors are used for. So the concept of a capacitor is kind of a simple one, in that we want to be able to store some charge on a device. Well, let's say that I have two plates here, and I have positive charge up at the top. Actually, I don't have any charge up at the top initially. Let's say I don't have any charge. But I connect these two plates to a voltage source, okay? And typically it would be a battery. Well, what's going to happen is, this is the top side of my voltage source, this is the bottom side of my voltage source. If I just connect a wire from the top side all the way to this plate up at the top here, all right, and this plate can be anything, metal or conducting, what's going to happen is the negative charge that might be on the top of this plate, if it's a neutral plate, is going to be drawn to the positive charge of the battery. Right? And on the bottom, right, negative charge is going to be pushed out to the plate on the bottom. So what you end up with is a bunch of positive charge at the top and a bunch of negative charge at the bottom. Well, in that case, what we have is we have an electric field, okay, and we have a net charge from one side of the plate to the other side of the plate. Well, what would happen if I were to disconnect this, all of a sudden. I just pulled the wire out, or I cut the wire, whatever the case might be. What would I have? Well, I would still have a plate with positive charge at the top and negative charge at the bottom. What if I now connected this to a wire and connected this to a wire, and I put some device in between here where the negative charge from the electrons at the bottom of the plate could travel up through my device to the positive plate? What would I get? Well, I would get some kind of current flow. And this is what the usefulness of a capacitor is. A capacitor allows charge to be stored between plates and allows current to flow from the negative part of the plate to the positive part of the plate when that charge needs to be used. Okay, so and that's essentially all a capacitor really is. Okay, so what are some of the characteristics of a capacitor? Well, it's really very simple. If you look over on the right-hand side over here, I've got a plate, a metal plate on the right-hand side. I've got a metal plate on the left-hand side, and in the middle, you can have anything. You can have an air gap. You can have a material in here that we call a dielectric. You can have really anything in there as long as it's going to separate the two plates. And as we'll find out in a little bit, having a material called a dielectric actually helps to increase the capacitance of our device. On the left-hand side, what we see is the actual construction of a capacitor. And because, as we'll find also in a few minutes, the area of our plates, right, makes a big difference when it comes to the capacitance of our device. The larger the area, the more capacitance. We try to maximize that area, and in here what we have is we have a bunch of a long area of some thin plate separated by a very thin dielectric with another plate on the other side, and it's rolled up. And it's rolled up so that we can have as much area as possible in a very small container. So if we want to define what capacitance is, right? The definition of capacitance is the amount of charge on a set of plates divided by the voltage across those two plates. Okay, so if I wanted to measure the capacitance and I had some way of measuring the charge on the plates, and I could certainly measure the voltage across those two plates, I could come up with the capacitance. Or if I knew the capacitance of a device and I knew the voltage across the plates, I could know how much charge is stored on them. So that's one way to actually do some measuring of the capacitor. Okay, another way that, or another thing that's quite useful to have as far as building a capacitor is a physical description of how a capacitor is put together. All right, and so there is also another equation that we're going to use for capacitance, and the capacitance of a device is equal to a constant k, and unfortunately we have to reuse the letter k again, small lowercase k. It's the lowercase k called the dielectric. So the letter k is defined as the dielectric value times another thing called the, didn't draw that E very well there, that's epsilon 0, that is the permittivity of free space. Okay, and that's how easily things can be conducted through free space, times the area of our plates divided by the distance d between the plates. So if we wanted to construct a capacitor, this is physically how we would construct it. Well, epsilon 0 is a constant. There's not much we can do there. Okay, so we can't really change that. But there are three things that we can change, can modify, as we go about designing our capacitor. One is the area. Okay, I can change the area, make it as small or as large as I'd like. And typically we want capacitors to be larger, and so we're going to have a large area. I can set the distance d. Okay, so I have these three variables. 1, the constant k, 2, the area, and 3, the distance between the plates, d. Okay, I can't modify epsilon 0, but I can modify the others. Right? The area is the area of the plates themselves. D is the distance, that's separation between the plates, and K is the dielectric value, which we can put between the plates that will increase our capacitance by some amount depending on what the dielectric value is. So let's try a problem. Let's say that I'd like to build a capacitor, a 1 farad capacitor. And by the way, the unit for capacitance is the farad after Michael Faraday. So I would like to build a 1 farad capacitor, which, believe it or not, is a very, very large capacitance. So 1 farad is going to be the size of our capacitor. Okay, and I've got some numbers here that I need to be able to use. So we would like to know what the area is going to be, or have to be, if my separation between the plates, the distance d, is 1 millimeter, so 0.001 meters, and the dielectric that we're going to use is going to be an air gap, and so the dielectric value for an air gap is 1. Okay, so let's do the math using our equation that we have up here. That's C. Let's move that up just a bit. There we go. C is equal to K times epsilon 0 times the area of the plates divided by D. So what do we got? So 1 farad, all right, is equal to K, which is going to be 1, times epsilon 0. Well, I haven't told you what epsilon 0 is yet. It's a constant that is 8.85 times 10 to the minus 12th. Okay, so this is K. We have epsilon 0 times the area A, which is what we're looking for, all divided by D, the distance between the plates, which would be 0.001 meters. All right, and after we do this on our calculator, what we find is that the area is going to be 1.13 times 10 to the 8th meters. Now, what's the problem with this? Well, the problem is that 1.13 times 10 to the 8th meters is an area in the millions and millions of meters, right? Is this practical? Not really, all right? This would be a very, very difficult capacitor to build, okay? It would be very, very large. So what could we do then, right, to make this more doable? Well, again, the equation is C is equal to K times epsilon 0 times the area divided by the distance between the plates. Well, what if I reduce that distance from 1 millimeter to 1/100th of a millimeter? All right, that would certainly help. Okay, and what if? So that's one thing that I could change. And what if I also put in a dielectric into this capacitance? Okay, let's see what effect it would have. Well, let's say that we still want to have our 1 farad capacitor. Okay, and now I'm going to find a dielectric which is going to have a value of 300. Okay, epsilon 0 does not change, so that's 8.85 times 10 to the minus 12th. Okay, times the area divided by, instead of 1 millimeter, it's going to be 1/100th of a millimeter. Okay, and let's see what we get as we do the calculations. Well, when we plug that into the calculator, what I get is 3.76 times 10 to the 3rd meters. Well, is this still realistic? Well, no, not really. But we're getting somewhere. Okay, we're getting somewhere. We've reduced it from 10 to the 8th meters to 10 to the 3rd meters, which is a big improvement. Okay. Now, one thing I have not covered yet is, why does a dielectric make a difference? So let's take a look over at the right-hand side over here. And on the right-hand side, I have a picture of a capacitor, or a diagram of a capacitor, that has the two plates, plate here and a plate over here. All right, and you can't really see that. Let's see if I change this to yellow here. That's better. Okay. Okay, we have our two plates, and in the middle what we've done is we've put a dielectric. Well, if I switch back to black now, if I have positive charge up at the top and a negative charge down here, and I put in some dielectric here, what are the molecules of a piece of paper or some non-conducting material going to want to do? Well, the molecules are going to want to align themselves just as they are aligned in the picture to the left, so that the negative charge is at the top, and I'm not going to be able to draw this very well. The negative charge is at the top closest to the row of positive charges up here, and the positive charge is closest to the negative charge down here. Okay, what does that actually do? Well, remember that I've got an electric field from the positive part down to the negative part down here. Well, if I now have molecules that have a reverse polarity on the inside, positive to negative, positive on the bottom, negative on the top, I have an electric field created in the dielectric that is opposing my electric field from plate to plate. Well, we all know that the voltage inside between this plate and this plate is equal to the electric field inside times the distance d. Well, if the distance d is a constant, right, what we've effectively done is reduce the electric field in here, right? If I reduce the electric field, I've reduced the voltage. Okay, now let's go back to the left side of the screen over here because I've got a little more room. What was the first equation that I had for capacitance? It was capacitance is the charge Q divided by the voltage V. Well, if I have the same amount of charge stored on the plates, but I reduce the voltage V because I've reduced the electric field E, I have effectively increased the capacitance of the device. And this is why a dielectric will cause the capacitance, or inserting a dielectric between the plates will cause the capacitance of the device to go up. Well, I hope that helps, and please see the video on problems with capacitance if you're looking to see some solutions to capacitor problems. Thanks, and have a great day.